Hi, everybody. Thank you for coming here for our presentation. I'm Hisashi Osanai, working on Monasca Analytics, a component of OpenStack Monasca. In these days, I have been analyzing a lot of customer data using Monasca Analytics. We share one of the use cases. Today, I have two of my colleagues here, Koji and Daisuke, becoming speaker regarding Monasca and Monasca Analytics after me. What I'm going to talk about is one thing, share our use case in details as much as possible. First of all, I explain the use case briefly. We improved alert management in Fujitsu Cloud. The Fujitsu Cloud is built based on OpenStack, and every service have been monitored by Monasca, one of the OpenStack service. The problem was operators got tons of alarm when a trouble happened, even if there is actual trouble in one service. I heard similar problems in past summit from operators who belong to different companies. This is a common use case. As a result, Monasca and Monasca Analytics eliminated unnecessary alarm. So we saved the operator from long investigation works. Here, I would like to explain two important backgrounds for the use case. Please look at left-hand side. There is a chart for the data usage from 2009 to 2020. In 2020, data became 40 zettabytes. So one important background is data size. Another one is complexity of infrastructures. Rapid progress of virtualization technology, such as VM, containers, and software-defined technology make complexity. What do you think? Is it really possible to understand everything in data centers? I don't think so. It's too complicated. So data and software-defined technology interplay lead to two things. One is slow problem resolution times, because it's hard to extract clear pattern to alleviate problem. Second one is redundancy, very similar solutions applied everywhere. Each vendor has own solution for the problem. So it's difficult to generalize common situations to establish widely applicable best practices. Why do we think about widely applicable best practices? The reason is realizing long-tail distribution. Operators don't want to use vendor-specific solution because of avoiding vendor locked-in. To achieve long-tail distribution, we need to follow two steps. First step is find and seeing problems in multitude of small, mid-sized installations. Then, need to share expertise and establish common practice for the problems. Here is the latest trend for this area. I usually use the word IT analytics, but nowadays the word was changed to AIOps platform. It stands for Artificial Intelligence for IT Operations. AIOps enhance IT operation using big data, modern machine learning, and other advanced analytics. And also, AIOps enable the concurrent use of multiple data sources, data collection method, analytical technology, and presentation technologies. Here, there are AIOps capabilities. There are 3 blocks. Left-hand side, there are monitoring-related capabilities, such as streaming data management, log data ingestion, wire data ingestion, and metric data ingestion, and so on. Upper right, There are analytics-related capabilities, automated pattern discovery and prediction, anomaly detection, root cause determination. Bottom right, there are delivery-related capabilities, on-premise delivery, software as a service. These information from Gartner, but I think infrastructure as a service is more suitable than software as a service from technology delivery point of view. As I explained before, operators have two issues. One is slow problem resolution times. Another one is achieving long-tail distribution. Regarding slow problem resolution times, machine learning helps time scale and complexity. Easy to extract common patterns. So operators can achieve speedy resolution of problems. Regarding achieving long-tail distribution, there is no solution to share expertise and define machine learning solution recipes. But I have a good idea. OpenStack community and Monasca Analytics can solve this. The goal might be self-healing from the problem, optimization such as resource management, power consumption. To achieve the goals, we have to make steps. First step is find out unusual behavior and root cause. Second step is collaborate with other services such as Nova, Neutron, and so on in order to make next action. Now, we focus on first steps such as anomaly detection, causal analysis. Okay, I hand over to Koji. Koji, could you explain the use case of Monasca point of view?
Yeah. Thank you, Hisashi. Hello, I'm Koji, and working on Monasca development team. And I'd like to explain about what Monasca is and story of introduction to the Monasca to the monitor Fujitsu Cloud environment. Sorry, Monasca is an official project of OpenStack, and Monasca provides monitoring as a service solution, which is well integrated with OpenStack, especially for the keystone authentication and Horizon GUI. Monasca can collect, monitors, and analyzes the metrics and logs of whole OpenStack environment. And Monasca is a scalable HA and high-performance monitoring tool. Roughly speaking, Monasca consists of two features. First part is monitoring, and the second part is analytics. Monitoring part has also two components. One is metrics monitoring, and the second is log management. I explain about the monitoring part, which I introduced to the Fujitsu Cloud environment at first. Here is the architecture of Monasca. First, I'd like to speak metrics monitoring part. Sorry. So metrics monitoring feature provides monitoring many types of metrics. So Monasca supports not only the system metrics, so like CPU usage, memory usage, or network traffic, or like that, but also a lot of applications, especially for the OpenStack environment. Of course, the OpenStack services like Nova, Neutron, Cinder can be monitored, and additionally, the middleware of OpenStack, so MariaDB or RabbitMQ, are also supported. Monasca can detect the problems which is running on the environment and starts to correct the metrics automatically. Monasca is well integrated with OpenStack. It can provide the cross-tenant monitoring. Monasca can provide the metrics of Nova instances, CPU, memory, and disk I/O, and so on, to each user who has the instance without installing the agent into the instance. This is the metric agent architecture. So metrics agent consists of 4 components. So collector and stats D forwarder, and supervisor D. And first, collector collects metrics periodically and has the plugin capability, which makes it easy to add supporting applications. The second one is the statsd. It can accept the metrics from the external as a demo. And forwarder sends the metrics collected by collector and statsd, and the supervisor D manages the processes above. And here is the Monasca UI. Monasca UI is well integrated with the Horizon GUI. And here is the login page of the Horizon GUI. After installing the Monasca UI and logging into Horizon, you can find the menu of monitoring in the tree on left side of the Horizon. And this is the overview tab of the Monasca. You can find the status of each component you monitored. And it's possible to draw down the status when clicking the services or servers or log passes. Here is the alarm tab of the Monasca UI. You can see the alarms which is related with the component which you clicked. And the alarm of Monasca is a little bit different from the other monitoring tools, I think. The alarms has the status, like here, OK, and the OK and high. The OK means no issue on the threshold checking written in the right side. And here is the high. It means the alarm status. And the alarm means the measurement exceeded the threshold. Monasca notified when the status is changed. Here is the dashboard for the metric. Monasca provides a customizable and very graphical dashboard. And next, I explain about the log management part. So log management feature provides this capability here. Collect logs from entire system and analyze the logs across all services which services with powerful GUI and alarm with some specific messages, for example, error or critical log messages. The log management is also integrated with Keystone authentication, and it can provide multi-tenancy support. Additionally, it can provide log messages which output into the OpenStack infra server, like neutron packet log to each tenant user who has a security group or firewall. Maybe I don't need to say about it to you here, but let me explain why log management is necessary. Recently, many systems are composed as microservices. Of course, OpenStack does. In the microservices system, the log files are distributed to hundreds of log files and to several machines. If you try to monitor the logs by traditional message monitoring, like Zabbix, of course, you can detect the machine where the error message appears, but it's quite difficult to trace the logs through some components. So it's very important to manage the logs in Central. Here is the log dashboard. This is also customizable and graphical UI, and supposed to trace and find the troubles from logs. From here, I'd like to show the story of introduced Monasca to our cloud environment. What was improved and what was problem? We have a cloud environment, let's call it Fujitsu Cloud. In Fujitsu Cloud, the controller components are deployed in separated virtual machine. And each component has two nodes to achieve the HA and maintenance. At first, we used Zabbix to monitor the environment. However, we had a performance problem of REST API in the environment, but we could not detect the slowdown. And it was very time-consuming to trace the log files of each node. So to solve these problems, we decided to introduce Monasca. For the first step, we introduced Monasca to controller nodes to monitor the API response and manage the log files of each OpenStack services in the Central. And we are monitoring the API response time with log and metrics agent. As you know, basically OpenStack components output logs by Oslo log, right here. And it contains the information of API response status and length and time. We developed the filter of log agent and picked up the value of time field and send it to the statsd as a metric with the Monasca statsd client. After that, metric agent sends the metrics to metric API. Here is the dashboard we created to monitor the API response time of each services. The boxes on upper side show the average of the API response time, and the graphs below are showing the changes of response times. The upper side boxes let us know a slowdown happens by turning orange red color. When the average of response time is over 5 seconds, it turns into orange, and over 10 seconds, it turns into red. And Monasca has notification capability and supports several notification types. Email, webhook, and integration with external services are supported. At this moment, Jira, Slack, PagerDuty, and HipChat are supported. Monasca notification has plugin capability, so it's not difficult to add the notification type. Maybe as you know, the Mattermost is a clone of the Slack, so it's possible to use Slack plugin for the Mattermost. We are using it. Here is the image of notification in Mattermost. API response time can cover the monitoring the system metrics like CPU memory we considered, so we set the notification only when the API response time is over 5 seconds. After I introduced Monasca, we became able to monitor API response time with Monasca. However, we got a new problem. So OpenStack APIs are related with each other component. So when only one component is in trouble, the other components also get affects and happen slowdown. In this case, not only the component which is the root cause of the trouble, but also the other components notify tons of alarms. So we got nearly 400 alarms in the trouble, but no need to care the services which were not root cause components. So it was quite a bothering task to check which alarm was the root cause alarm. I hand over to Daisuke. He is a specialist of Monasca Analytics and solved the problem I spoke here. Yeah, Daisuke, please explain a bit.
Thank you, Koji. Hi, everyone. I'm Daisuke from Fujitsu, and I'm working on Monasca Analytics development team. I'm going to talk about our challenge with Monasca Analytics for the problem which is explained by Koji. In particular, about Monasca Analytics, how to solve the problem, and results of this challenge. So let's begin. So I'd like to talk about motivation to solve the problem. The problem is the nearly 400 alarms related to OpenStack APIs are notified when trouble occurs. And the alarms bother operators. And then operators starts investigation for all alarms. But it will take a long time. Our motivation is operators to be focused on only what matters in troubles. If we can reduce the alarm, operator has no bother from tons of alarms and has no long time investigation works too. Reducing alarms brings some advantage to operator. One for operator, no needs checks for all alarms. And other for operator checks only root cause alarms. Therefore, the time of investigation is reduced. This point is that we'd like operators to focus on cause OpenStack APIs when trouble happened. Next, I talk about our challenge. Our challenge is alarm management with Monasca Analytics. I'll explain the detail of Monasca Analytics after next slide. In this slide shows the role of Monasca Analytics with simple figure. We have succeeded in reducing alarms by Monasca Analytics because Monasca Analytics solves about following points. When any alarms are notified to Monasca Analytics, Monasca Analytics can decide whether an alarm is necessary or not, because Monasca Analytics can detect root cause alarms. Finally, we detected only root cause alarms. So what is Monasca Analytics? Monasca Analytics is one of the Monasca's components since Newton release. It can analyze data from Monasca with machine learning and useful for anomaly detection and root cause analysis. Monasca Analytics has recipe, which is configure file, and machine learning solution can be described in the recipe. Monasca Analytics repository is following URL. So this slide shows Monasca architecture with Monasca Analytics. Like other engines, Monasca Analytics can be integrated with Monasca as an analytics engine. So Monasca Analytics can use metrics and logs data collected by Monasca as a machine learning data. So next, I talk about Monasca Analytics architecture. Monasca Analytics has a framework that can automatically execute machine learning processes as a data flow sequence. The data flow sequence is composed by following modules. In particular, data reception, preprocessing, aggregation, machine learning algorithm, and prediction. Data reception module can receive the data from various sources, like Kafka, database, and files. And data preprocessing module preprocess and transform data, like scaling and normalization. Data aggregator module aggregates data for machine learning algorithm. And machine learning algorithm module analyzes the data. And data prediction module predicts for the new data. And this module is able to add new module or customize, as long as each module follows the rule of the framework. For example, if user want to add new machine learning algorithm, it can add new machine learning algorithm modules. And the data flow sequence defines training phase and prediction phase. As shown is in figure, red line means training phase. After receiving past data as training data, Monasca Analytics preprocess it, aggregate it, and pass it to machine learning algorithm. And then blue line means prediction phase. This phase starts after learning phase automatically. After receiving data as a testing data from streaming data, the Monasca Analytics predict it directly. If test data needs pre-processing, test data can pass through data pre-processing. And then I explain detail of recipe. Recipe is a configure file which can define the data flow sequence. In other words, each module and phase are configured as a recipe. For example, if you want to execute only learning phase, you can create a recipe as a executing only learning phase. Recipe is one of the essential points in the Monasca Analytics because it means machine learning solution is reusable. In other words, once user can create a recipe which can get the best result, it can be reusable in other environments as well. So I will explain concretely how to solve the problem. We use machine learning to detect the causality of each alarm, and we notified only the root cause alarms. Specifically, Monasca Analytics collects a large number of alarms which related to OpenStack API and transform them to training data, and then train the relationship of each alarm and analyze the causality from training data. After training phase, prediction phase is started. When some alarms are notified, Monasca Analytics predicts causal and affected alarms from the causality of each alarm. So it was able to separate the alarm which is caused or which is affected. Finally, we detected root cause alarms. Let's see the process of Monasca Analytics. This slide shows training phase. First, consume list of alarms which are related to API response time from Kafka. The point is get various alarms patterns. Collecting many alarms patterns, you can create more accurate causality of each alarm. Second, aggregate alarms and transform to training data for machine learning algorithms. In other words, collect the training data sets necessary for machine learning algorithm to learn. Finally, in training phase, learning relationship of each alarm with machine learning algorithm. And then we get causality of each alarm. After that, shift to prediction phase automatically. First, consume list of alarms which are related to API response time from Kafka, just like a training phase. And then predict alarm to detect causal and affect. After receiving alarms, Monasca Analytics predict it directly because Monasca Analytics has already trained. Finally, push list of alarms to Kafka and notify to the Mattermost via Monasca. At that time, notify to the Mattermost to sort by causal alarms and affected alarms. Results of our challenge. In this case, about 400 alarms were notified before introducing Monasca Analytics. But we are now able to notify only the root cause alarms. So we could reduce the alarms to about 8. And unnecessary alarms are notified to another channel of Mattermost. So there is no need to check. Before introducing Monasca Analytics, relationship of each alarms was very complicated. For that reason, we checked for all alarms one by one and checked investigation is necessary or not. At that time, we were able to stop unnecessary alarms. But we had the possibility of missing of necessary alarms. After introducing Monasca Analytics, causality of each alarm is detected automatically. Therefore, we succeeded in reducing necessary alarms properly. For that reason, we hardly miss of the necessary alarms. Conclusion. In this case, before introducing Monasca Analytics, the number of alarms per trouble were 397, and now we could reduce to 8. It means that about 1/50th. Also, for the time of investigation, before introducing Monasca Analytics, we had took 5 hours and 30 minutes because we were checked all alarms. Currently, we can reduce to 30 minutes because we can focus on investigating the root cause. And now, we succeed in reducing the load of operator. Operator only needs to check the root cause alarms in troubles. And the investigation time has also been shortened. Finally, operator has no bother about unnecessary alarms. So that's all for our presentation. Thank you much for your kind attention. And now, we will try to answer any questions you may have. Once more, please.
Do you need machine learning to be able to exclude or stop receiving all the alarms? Can you just monitor 3 alarms? You know, Keystone, Neutron. Do you need machine learning?
We monitored all of OpenStack services, alarm from all of OpenStack service, and machine learning technique is used for only judge this alarm is root cause or not. After that, we back to Monasca, and Monasca use this information to present. In this case, after that, Monasca stopped the alarm, unnecessary alarm with their API. So this is the whole sequence.
How do you discover the root cause in the training phase? Is that an operator who has to say, this was my root cause, or does the machine learning automatically discover the root cause?
We use machine learning algorithms about Lingham algorithm.
What's the success rate? In the process, there's a rate of failure that the machine learning was wrong. What rate is that?
So first, we need to have all case of the training data. So then, if same case will be happen as a trouble, we realize this alarm is related to this alarm or something like that.
Okay.
So
if it's a new issue that the training hasn't seen yet, will it alert on all the alerts again, or will it try and filter them out? I'm concerned that operators wouldn't get a message if it's a condition it hasn't encountered before.
So in this use case, we didn't recognize the new case, but so we use so unsupervised technique So it might be possible, I think, but we don't know the actual case. Yeah.
Okay.
Yes.
As I know, the most important part of the machine learning is training, but the most important of training is data.
Mm?
I want to know where your data come from.
So Monasca gathered all of the data for Monasca Analytics.
I mean that the data you training your machine learning algorithm,
Mm.
where does the data come from?
So real environment, our cloud environment. So we have the cloud environment internally, Fujitsu. So we are introduced Monasca, the Monasca agent for the environment, and we are collecting the information from there. So the Monasca Analytics using the data from the Monasca. Yeah,
Meaning that you already have your customer data you can use for your machine learning. Your real environment or real.
Real our environment, but it's not our customer.
Sorry,
Internal Fujitsu, but from Monasca Analytics point of view, we have a lot of POC with real customer. So we have experiments, but in this case, so we need to use internal information because it's very easy to publish the information. So we use this use case.
That's all.